Yeah. All right, so our next speaker and the last one for this session, so for today, is Magnus Hellstrøm-Finnsen from Hochschild University College. Yeah, you can start if you like.
Yes, thank you very much for the introduction, and I'm also very grateful and happy to given this opportunity to speak. So I will talk about some work in progress on Hochschild cohomology of Monads. Today I think I'll mainly focus on some categorical combinatorics of how this can be, so how monads can be fitted into Hochschild's classical definition of this cohomology theory or algebras or rings of your warned. So let's recall this this theory of Hochschild. So was two papers in 1945 and 1946 that initiated this cohomology theory of algebras. So the combinatorial idea here is, so if you study maps from K tuple of the ring, so tensor with itself K times, into R itself, or more generally a bimodule, how can you get a map from a larger tuple? Let's say we add one more object into the same bimodule where the values are, and so the way you do this in Hochschild cohomology, I mean, it's many ways this can be done. Is, I mean, the procedure has mainly two parts. So you can multiply. Oops, oh, sorry about that. You can multiply adjacent occurrences of the ring. Yeah, and then you get the tuple of R. Then you get the K tuple, and then you can apply the map. So this is in some sense the inner part, and the outer part is you can apply this F on each side of the tuple. So you first the outer part, so we get then we get the value bimodule, which is then tensored with the ring on one side, and do the same on the other side. And this complex is then formed by taking alternating sums of all this stuff, both the inner and the outer on the two outer stuff. More generally, this can also be for algebras. I mean, it's not so much that go into this thing. So we have some kind of algebraic objects, which I mean, of course, maps, you will always have in categories and can tensor. And then, but you can active area in homological algebra where you use this to study dimensions of abstract algebras. But today we'll focus on categories. So I mean, it's so as mentioned, it's not so much that goes into this definition. So so more than half a decade ago, this is actually well understood by the business of universal algebra. So with a monoidal category and a monoid inside here, and you will of course have this. Perhaps it's a bit annoying part that you need at least a priori this alternating some things. So it should have some A/B categories, some enrichment in building groups. But I mean, this is perhaps not that bad. But still, you can do it for I mean very for do this for monoids and here you can also, I mean, this to study K algebra, so has some motivation from so we should have some perhaps some more that is not so dry at monoids, but there's some more. It will be good to have to study this categorically with some more structure, and there are of course ways you can manipulate the tensor product, which is done by using a Cohen. Then you can think of this as homotopically well-behaved tensor product for algebras, and that has been done by recent work by Catherine Hess and Alexander Berglund. So they were interested in homotopical co-algebras, I think. But it will be good if you, in some sense, of the idea I have, perhaps with self-promoting here, but the idea I had is if you can, in some sense, build this this stuff into structure over an object, and therefore this applies some motivation that you can study monads, and because there you have a map that respects the category you start with. So let's fix some notation. So let's see the weak pi category. So we have some notion of objects, which I will mostly denote by small Latin letters. We have some notion of one arrows between the objects, which I will denote by this. We have horizontal composition rule, and for each object we have a unit or a unit one arrow, which I will denote by this. So far, in the quite similar setting as original or usual classical category. And we also have some notion of two arrows between one arrows, which I will denote by double arrow and small Greek letters. And yeah, notion of vertical composition, so composable pair here, so we can get a new arrow, and we have also some notion of identity two arrows for each one arrow, and this should this should have relations and more maps. So I'll just mention a few of them. It's that the one composition is associative, but not on the nose, but up to a two arrow, which is invertible. And so now it's I mean, in this weak setting, if we are going to make tuples, right, we are in a bit different situation than in the classical theory notional left uniter. So this is false, but we have an invertible map that associates the identity composed with an arrow to the arrow itself, and the similar thing on the right. And there are also some more relations and many more conditions and diagrams. I think we'll be here tomorrow, which we should go in detail. So, and I mean, it's quite late in Australia now, isn't it? So, tomorrow is not so many hours away, but so bad analogy. But yes, anyway, the things there. I mean, perhaps most important for us here is how we can relate the vertical composition with the horizontal composition. So we have a procedure of doing that. So yeah, I will not go into that, but I think that's important to have in mind. And we have this bit annoying detail, which for now is that this one homomorphism category. So there are categories on their own right, with objects are one arrows and arrows are two arrows. We require this to be AB categories. So the morphism groups here are abelian categories. Morphisms that are abelian categories. So let's go to monads and modules of monads. So by monad, I mean an object A together with a one arrow T and two arrows, a multiplication rule that associate T composed with itself with just T itself, and a unit which will act as a unit for this multiplication that is a relation from the unit of A to T. So this should satisfy two diagrams. So this diagram, I mean that the unit is two-sided and the multiplication respective. So if you take this unitary relations in the bicategory or the unit or the multiplication, and then apply the multiplication map, then we get the same catching. And we also require the multiplication to be associative. So here I choose to have the parentheses, started parentheses on the left, which actually means that I compose from the right. But so perhaps intuitionally it would be better to have it opposite, but yeah. Anyway, so if you first apply the multiplication map or secondly on each side, this diagram with associated communes. So left modules. So now I add an arrow to the left of A. It comes with an relation that associates X first, then composed with T to X itself. And this, I mean, this thing has some street cred, so it respects the units, and it's also associated. So I mean, it acts associatively with the multiplication map. So there are two diagrams here I choose to skip. And similar for, I should also mention that in literature, left modules or monads are often called T algebras. And similar for the right module, so now I have an arrow on the right of A, so the right side of T, and then I have this action or relation omega, so two arrow that associate T composed with Y into Y itself. So it also respects the right unit and it's associated as the same thing as for left modules. So in the classical definition, we wanted to or some we want or Hochschild wanted to values in a bimodule, which I define here. So if we let so a bimodule which consists of data Z, sigma, and omega. So Z and sigma is a left T module, and Z and omega is a right S module. So here we have S on the left, T on the right, and you should respect these two. So the relations goes like this for this chain above. And we also that these two, so sigma and omega in the bimodule, they should have, so they have if you take sigma first or then omega first or opposite, this should be the same thing, or it's varies up to the associate. So I mean, now we are in a good shape situation. So we have this algebraic object, and we can now see how it fits into this combinatorics or Hochschild homology, and we can form this homology chain. I should also perhaps mention here that these T opposite algebra, bimodules and T algebras, they are actually living in another category than T itself, since the one homomorphisms are categories on their own. Right, of course, is in the same bi category, but I mean this is something yeah, seems to give some flexibility. And today I will be rather boring and focus on T bimodule as in the classical definition, but I also looked at if this is not the case, and we can also have some relative versions here, which was interesting, but it looked a bit exclusive. I think it works, but it looks a bit exotic to like fit into the framework of Hochschild-Cohomology. So yeah, so we need these tuples first. Where I choose to arrange all parentheses, so we go into the depth on the left side here, and you actually start to compose on the right side of the chain to form this tuple. So and we should look then at maps into bimodule set. So doing this, we can form this chain of two homomorphism groups. So on the left, you are on the zeros, and then the zero position. We look at maps from the identity. So this is sometimes the zero tuple into Z, and so there we should have a differential that take maps here into maps from T to Z, and for the higher groups in the chain, we have K tuples that should take maps into from K tuples to Z to K plus 1 tuples into Z. So let's take the first differential first. So we look at phi from the identity of A into Z, and we should now form map from T into Z, and that's by taking the alternative sum of two objects. So if we first, so we should start at T, and we get the unit on the left side here and the unit on the right side here. We apply the map on each of the side with the unit, and this thing here, it looks strange, doesn't it? That you have maps composed horizontally and then vertically. How this can, but this is one of the relations between horizontal and vertical composition that make this work. That yeah, I mentioned that we didn't draw this diagram. And for the higher cohomology, yes, you take. So this is the outer part. So here you have to arrange the parentheses. So we get this this t here free, so we can apply phi on this tuple. On the other side, for the outer part, you have this by how we define this tuple. So here is automatically, and so this is a arranging of parentheses. You apply the associator in the depth of the tuple many times, and you got eventually this, and you apply phi on both sides. And you also, for the inner part or the middle part, you also have some arrangement of the parentheses, but here you can apply the associator directly on the right level. So I mean, you don't care if it's so we want to isolate a double tuple that you can apply multiplication method to, but we don't care if it's in I mean in the depth. So this actually form, so the alternating sum of this, that's the differential. This form coaching complex, and this is how we define the cohomology groups. So I think I'm running out of time now, right? So let me just mention some, skip this, that you can form a cohomology ring like this by taking the sum of all the groups. And when we pick representatives from each part of this cohomology ring in degree n and m, we can define a coproduct, which then gives a map from degree n plus 1 into t. So I mean, this is representatives for the quotients in this group. And this actually, so this is some details about how this product is defined, but this makes this so with this coproduct makes the cohomology ring graded commutative. So thank you for your attention.
Okay, so we can thank the speaker. And are there any questions?